This is the second half of chapter 9, and right now we're looking at the relationship between two time series in the frequency domain. So we're going to start off by defining another time domain concept. We just saw the cross correlation function. So there's a comparable cross covariance function, which we don't normally look at. It's normally easier to look at the cross correlation function, but the cross covariance function can be useful for constructing the frequency domain quantities that we need. So here's the cross covariance function. Gamma xy of h is the covariance, not the correlation. So let's just correct that typo. Is the covariance of xn plus h with yn. It's often a little bit hard to remember if it's the covariance of xn with yn plus h or xn plus h with yn, but this is how it's defined. And the cross spectrum is the Fourier transform of this quantity. So we're going to call this lambda xy of omega is the Fourier transform of gamma xy of h. And this cross spectrum can be obtained by smoothing the bivariate periodogram using spectrum in R. That's really a natural bivariate extension of the univariate spectrum that spectral estimation that we've seen before. Now, just like we don't normally interpret the covariance, we normally seek to interpret correlations and variances. The cross spectrum, we don't normally look at it. We normally scale it to be a correlation at each frequency, and so this is the this is called the coherency, and there's another typo because this should not be squared. People often look at the squared coherency, but here I've written the plain coherency. Measures the correlation between frequency components of two time series at each frequency omega. Now this thing is complex valued, and so like a complex number can be represented as a magnitude and an angle, and that's the way we normally interpret it. The magnitude has a name called the coherence. So this says whether a large amplitude at frequency omega for one time series is associated with a large amplitude for the other one. And so that's kind of a correlation of magnitudes. And the other part of the complex number is the angle viewed as a number in the complex plane. And this is called the phase. So if the phase is 0, that means that peaks at frequency omega occur simultaneously. So the two processes xn and yn are in phase at that frequency. If a phase of plus or minus pi is entirely out of phase, so when x has a peak, y has a trough. And so once you can estimate the bivariate periodogram, you can smooth it and estimate the coherency, and then take the phase and the coherence, and then becomes a question of interpreting these things. So let's have a go at doing that. Here is the code to calculate the coherency and phase. So what we do is we calculate the bivariate spectrum smoothing very much as we did in the univariate case, but then we set plot equals false because we don't immediately want to plot that. We want to then construct the coherency and phase plots, which we do here, starting with the coherency. And R calculates squared coherency, which is formally squared absolute coherency, because coherency is a complex number. And this is very much like reporting R squared for a regression rather than R. So it's basically the square of a correlation. And let's see what this plot tells us. The blue band is a pointwise 95% confidence interval. So this is the estimate. And this is pointwise 95% confidence interval. And so let's say we see that the coherence is strongest. I'm going to look at the period rather than this looks to me like the strongest coherence at a period. It's roughly 1 over the frequency, which is 4, and this is in cycles per year, so the period is in years. And interestingly, this is around the length of a business cycle. We are not going to get too technical about that. Economists might think there are different business cycles of different lengths, but if you just think of lengths of booms and recessions, maybe that's about right. And previously, when we were looking for business cycles, we didn't find clear evidence of a peak in the unemployment spectrum at this frequency, but we find a peak in the coherence. So let's say perhaps business cycles show more clearly in the relationship between variables than in the marginal properties. Okay, so perhaps for our immediate question of looking at relationships, lead-lag relationships, the phase is more important for us than the coherency. So let's look at the phase. Here's the phase plot, and I put on a horizontal line at phase 0. This corresponds to unemployment and life expectancy oscillating in phase. And so we see that at most frequencies, phase is close to 0 at most frequencies. At least 0 phase is well within the 95% confidence interval. There's one exception, which is going on around here. Frequencies at around 0.4 cycles per year have more variation. But if we go back and look at this plot here, we'll see that at this point, the coherency is close to 0. And when a complex number becomes close to 0, its angle becomes undetermined. And so it may not be surprising that the phase is unstable. Let's say but coherency is small at this point. As coherency approaches 0, the phase becomes undefined. Okay. So now we can draw our kind of preliminary conclusions from the analysis we've done so far. There's strong evidence of procyclical mortality at a national level in the USA. This, I think, was from 1948 to 2018. And as just one example of this, the Great Recession of 2009, 2010 certainly had high unemployment and a lot of economic suffering, but these 2 years had above trend values of life expectancy at birth. And you can ponder why that is. We've argued that this evidence supports a claim that above trend economic growth causes above trend mortality. And that's because it can't be the other way around. And we've kind of defined it, so we're not trying to say we know what the exact variable is, but it has to be something going on in the economy, I guess. What we can't do at this point is say exactly what that variable is. We can't infer that unemployment reduces mortality for those who lose their jobs. That's actually not true. You can study unemployed people and find they have various health effects, including adverse health effects, including higher mortality. But this can be reconciled with a population level result that goes the other way, and that seems to be how things are. To get deeper into this phenomenon, you might want to look at results at a finer level. So panel data analysis just means putting together a whole lot of time series. So if you had time series for each state, you might get higher resolution to answer some of these questions. And that's kind of what happens. That's beyond this case study. So now we're going to go and check a few of the assumptions that went into the main analysis that we showed you before. Like, I didn't justify why I'd used an ARMA 10 error model rather than some other model. And so let's go check that. We can do our AIC table for regression with ARMA errors to see what that indicates. And here's the code. It's really very similar to the code for regular ARIMA, but we now put in the covariates XREG. And here we see what we get if among small models, ARMA 10 looks pretty good, but some larger models have better AIC. The ARMA 3.1 in particular has good AIC. I think that's the Well, that's almost the lowest AIC. There's a minus 79.91 here, but that's a considerably bigger model. We're going to let's look at the ARMA 3.1. If we compare this to ARMA 4.1, we see that adding one extra parameter hurts our AIC by about 6. So that's not mathematically possible if everything, they're nested models, so it shouldn't be able to gain more than 2 points of AIC. So, well, let's see what's going on with this our regression with ARMA 3.1 errors. We can fit the model, and we get an MA1 of -1. This should be reminiscent of the previous analysis we did of the Huron depth data when we fitted a larger ARMA model and got a fitted model that was on the edge of invertibility. And so I guess, these are not specially selected time series. I think this is just a common thing that arises in time series analysis. So this, although I'm not going to do here all the analysis we did for the Lake Huron data, we can probably anticipate that if we did, similar things would apply, and we might well find that Fisher confidence intervals are not so reliable, certainly not for the MA1 coefficient, and so perhaps a likelihood ratio test should be preferred. Well, another thing you can check when you do data analysis, if you find a relationship, you can ask, is it consistent through time? And you can repeat the analysis on say the first half of the data and the second half of the data and see if you get a consistent finding, which here I've done. This is, I think the results are indeed reasonably consistent in this 71-year interval. If you look at the data, you'll see the pattern seems weaker in the 1990s, but then it's quite evident again in the early years of the 2000s. So it passes that test of consistency through time. Another thing you might want to do, you should do really, is to plot the residuals and see if anything shows up. And here we go. Here's the residuals. One thing you see from this is possibly some decreasing variability. So I'm just looking at this and I'm thinking the residuals have larger magnitude earlier on. Who knows if that's a real thing? One could look into it. It makes me think that there's going to be some pretty crazy residuals going on when the COVID data starts getting into these analyses. It's not here yet because it takes a while for mortality data to be kind of processed and enter the human mortality database. So we're a couple of years out of date on that one. But I expect variability to increase again. Here is an autocorrelation function for the residuals. And so we see here that most of the ACF points are within this testing region for testing the white noise hypothesis. One lag is just outside, but it's not a major violation to have 1 out of 18 lags narrowly outside under the null hypothesis of Gaussian white noise. And it may not surprise us that there's some very small indication that there might be room for improvements over an AR1 model for the errors, because we know from the AIC table that the bigger models can find some advantage. They can find something to fit. Well, there are many other analyses you could do. Somebody might say, does it matter that you HP detrended? Maybe you should do something else. In particular, you might consider taking temporal differences. It's a traditional thing to do in time series is to detrend by taking differences and then analyze that. I think it's interesting to see what happens if you do that. Let's let delta En be En minus En minus 1, and then you can plot the difference life expectancy instead of the detrended. And I think you see that maybe there is a pattern, but it's not so clear as the detrended. And well, we can do again, we can check that by a statistical test. And the relationship between unemployment and life expectancy is also harder to find by statistical methods when you difference. And here's exactly the same model, but on differenced life expectancy. And you see there that the Z statistic for the relationship is 2.17, which is considerably weaker evidence than the 3.94 that we had before. So it seems that differencing destroys some of the pattern that we have that can be found. Well, this raises a question of is it fair game to try many different models and methods and look for the strongest relationship and report that one. Now, there's a clear hazard to doing this, which is called the multiple testing hazard. But before we get to the hazard, I want to point out a different scientific principle, which says that positive results are often more trustworthy than negative results. And a positive result of rejecting a null says something's going on. Very often, if you mess up the analysis or you look at the wrong thing, you lose the signal rather than creating a fully spurious signal. And in particular, if you're doing scientific experiments and you don't find evidence of an effect, you might have done a bad choice of experiment. You might have carried out the experiment poorly. If you imagine that if you're testing COVID vaccines, right, you might test the COVID vaccines different ways. Some ways it doesn't work. Then you find a way that it does work, and it's that positive result that excites you more than the negative results. And this has to be balanced a little bit with considerations of multiple testing. So if you make 20 hypothesis tests, you expect one to be significant at the 5% level just by chance. So when you do try multiple things, it becomes more important maybe to look for a little bit more, a stronger effect to compensate for the fact you looked for many things, and checking that the effect is consistent across time intervals and maybe across data sets is all good stuff to do. And one thing to do, if you do try multiple things, you should report that you did try multiple things. And the other thing to bear in mind is that if somebody found something from one data set and you then want to generalize it, you probably want to wait until it's confirmed in other studies, treat it as tentative until that time.